Hi everyone. Okay, so in this video, we're going to be talking about the symmetric group. So the symmetric group is sort of the most basic example of a Coxeter group. And it's sort of an example in which you can see almost all of or maybe a lot of the complexity of Coxeter groups in a very concrete way. So we're going to begin by introducing the symmetric group. We're going to do some examples. And then as the course goes on, we'll come back to this example very frequently. Okay, so the definition, so the symmetric group Sn, so that for each n and for each natural number n, there's a symmetric group. So the symmetric group Sn is the set of bijections, F is a bijection, it's a set of bijections from this set to this set, back to itself. And I should have written, this is by definition the set of numbers 1 through n. So an element of the symmetric group is just a bijection from the set of numbers 1 through n back to itself. That as a set, that's what it is, but it's a group, and so it has a binary operation on it, which is function composition. So if I have two bijections from the set of numbers 1 through n to the set of numbers 1 through n, then I can just compose those things as functions, and I will get another bijection. And this forms a group called the symmetric group, and the elements of the symmetric group are called permutations. So given any permutation sigma inside of Sn, there's going to be various ways to sort of write down this bijection, various nice shorthands for writing down this bijection that are sort of going to be useful in different contexts. And so the first one is the one-line notation for sigma. And it's just the ordered list of numbers, sigma of 1, sigma of 2, all the way through sigma of n. So if you want to know where does 1 go, well, it's just the first number. Where does 2 go under sigma? It's just the second number in the list, etc. Okay, so for example, S3. Okay, so S3 is the set of bijections, as a set, it's a set of bijections from the numbers 1 through 3 to the numbers 1 through 3. And so here I've drawn out all possible bijections. So for example, this denotes the function which sends 1 to 1, 2 to 2, and 3 to 3, whereas this is the function which sends 1 to 2, 2 to 1, and 3 to 3. Amazing. Okay, so the one-line notation, and so it's maybe a nice exercise, maybe I should have written this down, it's a nice exercise to show, let me write it here. So it's a nice exercise to show that the size of Sn, the number of bijections, is n factorial. So the number of bijections from the set 1 through n back to itself is n factorial, and here S3, so the size of 3 should be 3 factorial, which is 6, and indeed there are 1, 2, 3, 4, 5, 6 of them that I've written down. Okay, so the one-line notation for each of these permutations I've written below. So the one-line notation for this permutation is 1, 2, 3, because remember the one-line notation, how I get that, I just look at where does the function send, where does the permutation send 1? Well, it sends 1 to 1, and so I put 1 first. Where does it send 2? I put 2 second. Where does it send 3? It sends 3 to 3, I put that third. Whereas here, right, 1 gets sent to 2, so I put that first, and then 2 gets sent to 1, and I put that second, and then 3 gets sent to 3, and I put that third. Let's do one more. So here, 1 gets sent to 1, so I'll put that first, and then 2 gets sent to 3, so I put that in the next slot, and then 3 gets sent to 2, and I put that in the third slot. So hopefully that makes sense. And you can check for the rest of them. Hopefully I've done that right. So that's as a set, right? That's what S3 is. But S3 is a group, so its group operation is function composition. So let's do a couple examples of how this works. So if I do 2, 1, 3, that permutation, compose 3, 1, 2, what this means is you do this one first, because we're composing them as functions. So maybe I should write that here. So do this first. This first. So how do I figure out where 2, 1, 3 compose 3, 1, 2, what permutation that is? Well, I should just look at, it's just a function, so I should just look at its value on each number. So let's see where does 1 go under this bijection, so under this composition. Okay, so the first one sends 1 to 3, and then the second one sends 3 to 3. So that means that in total the composition will send 1 to 3, so I put a 3 in the first spot. What about 2? So the first bijection sends 2, first permutation sends 2 to 1, but then the second one sends 1 to 2. So that means altogether 2 will go to 2, and so I put 2 in the second slot. And then finally, where does 3 go? Well, 3 goes to 2 in the first bijection, and then where does 2 go? 2 goes to 1 under the second bijection, so altogether 3 will go to 1. So that means in total we end up with a permutation 3, 2, 1. And in general, this is how you compute this kind of thing. Let's just do, for fun, let's do the other way around. So here we did 2, 1, 3 times 3, 1, 2, and now let's do 3, 1, 2 times 2, 1, 3, so the opposite order. And you can check, good to get your hands on computations like this, that this is 1, 3, 2. And so you'll notice that these are not the same bijection, which means already S3 is not an abelian group, and in general Sn won't be an abelian group either. Which sort of makes it, it's maybe the first example of a non-abelian group that we see in like a group theory course, and now we're going to dive into the combinatorics of it. Great. Okay, so for those of you who are somewhat new to group theory, a great exercise is to show that Sn with the binary operation of function composition is actually a group, and that the identity in one-line notation is just 1, 2, 3, all the way up to n. This is just sort of confirming what we said on the previous board. And then for the rest of the board, we're going to discuss another way of writing down a permutation, which is called the cycle notation of the permutation. So to get started, we have, there's another great exercise to do, which is to show that there's a faithful and transitive left action of Sn, the symmetric group, on the set of numbers 1 through n. Which is given by, just given the way that you would expect, if I take a permutation and I take an element, or I take a number between 1 and n, then I just apply the permutation to that element. And so the exercise, I guess, is to show that this is actually a group action and that it is faithful and transitive. So this is another great exercise if you're sort of somewhat new to group theory and want to get your hands on the concepts and review them. Great. So given this action, we can introduce the cycle notation of a permutation. And the definition may look a little bit complicated, but on the next board you'll see that actually it's pretty easy to compute the cycle notation. It's just sort of difficult to write down rigorously. Okay, so for our permutation sigma, let's define this angle bracket sigma. This is the cyclic subgroup of Sn generated by sigma. So I put cyclic, so this is just the subgroup of Sn generated by sigma, and then it happens to be a cyclic group. And so this consists of the identity, and then which is sigma to the 0 power, and then sigma, which is sigma to the 1, and then sigma squared, and sigma cubed, etc. And then because Sn is finite, at some point this will all just end up back with the identity. And then that is the subgroup of Sn generated by sigma. And so what we're going to do is we're going to take this subgroup, so this is a subgroup of Sn, and we're going to restrict the action here to this subgroup, and we're going to let O1, O of 2, or O sub 1, O sub 2, up to O sub k be the orbits of that restricted action. Great, okay, so then for each one of these orbits, let's let AI be the smallest element of that orbit, right? These are orbits of an action on the set of numbers 1 through n, and so each one has the smallest number, and we're just going to let AI be that smallest number. And without loss of generality, we can just sort of reorder the orbits so that A1 is less than A2, which is less than A3, etc., less than AK. So right, in particular, this means that A1 is just 1, right? Because 1 is smaller than everything, and 1 has to appear in one of the orbits, because the orbits partition. Great. Amazing. So then now we can just say the cycle notation of sigma is this. So it's, we write parentheses around each, so each set of parentheses consists of the elements of an orbit, and then the elements are just written in the order that sigma acts on them. So I write A1 here, which is just 1, of course, And I write sigma of A1 next to it, and then sigma squared of A1 next to that, etc. And then at some point I'll just wrap back around and get A1. And then for the next orbit, A2 is the smallest element of that orbit, and so I take A2 and I apply sigma to A2, and then sigma squared to A2, etc. And at some point I'll just wrap back around. And I just do that for all the orbits. And that's the cycle notation. And sometimes we omit cycles of size 1, as I'll show you on the next board when I do a bunch of examples of this. Great. Okay, everyone, so now let's do an example of computing the cycle notation of a permutation given its one-line notation. So here I just cooked up some random permutation in S8. In one-line notation, it's 2, 3, 1, 5, 6, 7, 4, 8. And let's try to compute its cycle notation. So what we do is we start by just opening a parentheses and putting the number 1. And then we just see where does 1 go under this permutation. Well, I've written the numbers before the permutation up above just for convenience. Sometimes that's called two-line notation. So let's see where 1 goes under the permutation. Well, 1 goes to 2, so I write a 2 here next to the 1. And then we see where does 2 go? Well, 2 goes to 3, so I put a 3 here. And then let's see where 3 goes. Well, 3 goes to 1, and so since 3 goes back to 1, and I've already written 1 in that cycle, I close the parentheses, right? So this means that 1 goes to 2, 2 goes to 3, and 3 goes back to 1. Great. So to compute the next cycle in the cycle notation, I just pick the smallest number that isn't already in the cycles that we've done. So in this case, it's 4, and let's see where 4 goes. So I write a 4 here, and 4 is sent to 5, so I write a 5 next to it. 5 is sent to 6, so I write a 6 next to that. 6 is sent to 7, so I write a 7 next to that. And then 7 is sent back to 4, so I write a 4. And since I've already written a 4 here, it wraps back around, and I can just close the parentheses. And now I pick the next smallest number that isn't already written down. In that case, it's just 8, and 8 goes to itself, and so I just close it off in a single parentheses. And that's the cycle notation. And you can kind of see that given cycle notation, you could come up with one-line notation as well, just by seeing, well, cycle notation says 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, 5 goes to 6, 6 goes to 7, 7 goes to 4, and 8 goes to 8, and you can just write down that in one-line notation, which obviously would be this. Great, so sometimes we don't actually write the 1 cycles because you can sort of recover if you don't write the 1 cycles, you can still recover the permutation. And so maybe I'll just send it in a different color. So you could also write this as 1, 2, 3, 4, 5, 6, 7, and that's pretty standard. That's what most people do. Okay, so let's now compute in S3. We already had all the one-line notation for all the elements of S3. Let's compute their cycle notations. So 1, 2, 3, the identity gets cycle 1, cycle 2, and cycle 3. 2, 1, 3, I have the cycle 1, 2, close the parentheses, and then just 3 by itself. This one is just 1 by itself, and then 2, 3. These two things are what's called 3 cycles, as we'll see below. So this is this in one-line notation 2, 1, 2, 3, 1 is in cycle notation 1, 2, 3, and the rest are very similar. Great. So we can sort of one way of some data that you can get from the cycle notation is called the cycle type of a permutation, and this will be really important for computing conjugacy classes in the symmetric group, as we'll see in a few minutes. So what is the cycle type of a permutation? Well, let's take the orbits of the orbits of the action of the cyclic subgroup generated by sigma on the set of numbers 1 through n, the same orbits we were looking at before in the previous board. Let's instead order them by decreasing in size of orbits. So then the cycle type of sigma is just this string of numbers that's the sizes in decreasing order. And because they're in decreasing order, this is a partition of n. If you're not familiar with partitions, it's actually in another one of my videos in the POSET playlist, so you can go check that out. Great, so then a permutation is called a K cycle if its cycle type is just K and then a bunch of ones. And a 2 cycle, so when K is 2, this is called a transposition. And a 2 cycle so a transposition that's of the form I plus 1, that just interchanges I and I plus 1, and then does nothing else to anything else because the rest of the cycle lengths are all 1. That's called an adjacent transposition. And this terminology is going to be really important in Coxeter group theory, as we'll see. Okay, so let's compute the cycle type. Oh, I didn't even write down here. Let's compute the cycle type of this thing, and then the cycle type of everything in S3. So, the cycle type of this thing, well, okay, so what's the largest orbit size? It's 4. So the cycle type is 4, and then the next largest one is 3, and then the next largest one is 1. So this has cycle type 4, 3, 1, and then you can see in S3, right, for example, the identity element has cycle type 1, 1, 1, because there's a 1 cycle, 1 cycle, 1 cycle. These two, these are transpositions because they have cycle type 2, 1, so they're 2 cycles, and that means, by definition, that's a transposition. But these are actually adjacent transpositions because this swaps 1 and 2, and 1 and 2 are next to each other, and this swaps 2 and 3, and 2 and 3 are next to each other. 3, 2, 1, this permutation is also a transposition. It swaps 1 and 3, but it's not an adjacent transposition because 1 and 3 are not next to each other in the numbers 1 through n. And then these two are 3 cycles, as I said previously, because they're of the form 3 and then a bunch of 1s, although there's no 1s at all. Great.